My name is Noah Finkelstein. I'm a professor in the physics department at the University of Colorado at Boulder. My specialty is in physics education research. That is, I study conditions that support or inhibit student learning and the nature of student learning within the field of physics. I'm also a director of the Integrating STEM Education Initiative at the University of Colorado, which is an initiative that brings together scholars from the disciplines of physics, astrophysics, chemistry, biology, geoscience, engineering, math, applied math, with folks from the School of Education to focus on how students are learning within their own disciplines. That is, this field of discipline-based education research is growing tremendously now, and scholars within each of these disciplines are beginning to focus on how students learn within their disciplines. We're demonstrating that students who are in our courses are not learning what we thought them to be. We are finding that students in our large-scale introductory courses are leaving their courses, and they may get A's, but in fact we can demonstrate they don't know the physics the way we thought we had, and that's because we're taking a scholarly approach to understanding how is it that students are learning. We're actually now investigating, are students learning? We're using research-based and research-validated measures to understand whether our students are learning. And it turns out, for our traditional lecture courses, students learn 1 in 4 of the most basic physics concepts that they don't already know when they come into the classroom. That's not sufficient in my book for a quality education. By international standards, our students aren't achieving, and whether that's at the K-12 system or at the college system. Even at the graduate level, students in our elite disciplines, engineering and science, mathematics, are being outpaced internationally. And not that I'm big into this race game of the US outperforming every other country, it's just that we don't have the number of students coming out with PhDs in math, science, and engineering that we need to support our own country's infrastructure. And so now Europe and Asia are outpacing the United States in terms of PhD production. And while I'd love to live in a globally flat society where anybody can move anywhere, that's not the case. We must be educating our students within the United States. We must be supporting the development of our students here for our own welfare, as well as for the benefit of these students themselves and quality of life and creating an improved society. It's become apparent that we have a tremendous shortage of teachers in our K-12 system to adequately educate our students. 2 out of 3 high school physics teachers has neither a major nor a minor in physics. And while having disciplinary content knowledge is not sufficient, it is certainly necessary as a condition to be able to teach. So this is what we do, is not only do we recruit and prepare our best physics majors to become high school teachers. At the University of Colorado, we've tripled the number of students going into high school teaching, and those are our elite students. Those are our students who know the field the best, and they're helping us solve a grand national challenge. And unfortunately, in our traditional courses, students walk out of our classes thinking physics has less to do with the real world than when they came into the class. That's what we taught them. But now that we're measuring that, we can change our classrooms so that we teach students that physics is a study of the world around us by engaging them in real practices and real problems rather than simply contrived back-of-the-chapter problems for many of our textbooks. And in fact, our textbooks are improving based on these measures and assessments. So there's conceptual understanding, there's attitudes and beliefs, there's problem-solving skills, there's logical deduction and mastery in our class. Are they also able to use some of the key tools and principles in science, such as mathematics and graphing and analytical formalisms? So we can measure all of these things and see what the impact of our instruction is. Through the use of technology and to apply these research-based techniques that are grounded in how students learn, which is by building on what students already know and engaging students in their own educational practice through interactive techniques. Our students learn more now at the University of Colorado. They learn 2 out of 3 of the most basic concepts that they don't already know, almost tripling the national averages there in terms of learning gains in our classes. And we're not satisfied with that. We're looking to continue to improve that. Simultaneously, our students are actually learning more about the nature of learning itself, which is why they're becoming better learners. They're learning more about how to think about science and the nature of science in its own right. So we're engaging, we're building on this scholarship that really is a long-standing history in cognitive science and education. We're importing those ideas, we're building on those ideas, making them relevant, building new educational practices that really work in our physics classroom. And the fundamental points behind that is build on what students already know, value the knowledge that they have, engage them into educational practices so that they become owners of learning themselves. So rather than being passive recipients of knowledge that's being thrown at them and disseminated, students have to wrestle with ideas, make sense. Instead of becoming answer makers, our students are becoming sense makers. Our students are now engaged in the educational practice, which also tremendously helps with their motivation, their learning, and even the retention in the field. We are all ambassadors for our discipline. We're all sharing the beauty and richness of our discipline with others. And the more we do that, the better we understand the nature of our discipline itself and the scholarship that we're engaging in, the traditional research that we're doing. And the more we turn others on to the rich opportunities that lay within these fields. So by going out and working with kids through outreach programs, whether it's 4-H or Boys and Girls Clubs or demonstrating photonics and optics, it's such a natural way to look at the world. You can turn children on into a rich career, a rewarding individual life, and bring the next generation of scholars that we so desperately need. The best advice that I could give to students as they're engaged in the development of their own career is to be passionate about what you're involved in, to be motivated and work hard at what you're interested in, and to be your own advocate. To go out and find opportunities. There are rich opportunities. SPI is full of networking opportunities. Find somebody who's doing something related to what you're interested in. Chat with them about that. Find sessions that you're involved in. Participate in the mentoring program. Become your own mentor for others, which is go out and be an advocate. Participate in the SPIE outreach programs. SPIE offers you a professional society and a network that you can participate, that you can carry with you for the rest of your life. It'll enhance your own career and contribute to the career of others.